everyone. It is my great pleasure to speak here. And I'd like to thank all the organizers for their hard work, especially Vadim. Okay, anyway. So today, I want to tell everyone what is our plan about building Quantum Annealer version 2 and what's going on in the Quantum A.I lab in terms of building Quantum Annealer. Of course, nothing can get it done without a wonderful team. I have a great pleasure to work with all the researchers in Quantum A.I lab as well as users and Barbara. Especially, I want to give acknowledgement to all the hard workers who directly work on the Quantum Annealer project, particularly Chris Quintana and Davir Kafri, as well as Alireza Shabani, who's here in the audience today. So here's a quick outline of my talk. After a quick introduction, I want to tell you, towards building the Quantum Annealer version 2.0, what we understand so far, and what is our current hardware development, and what is our future plan towards building a larger scale Quantum Annealer. All right, so in Quantum AI lab, in hardware group, we are approaching two approaches. Of course, the fundamental goal is, the ultimate goal is to build a universal quantum computer with error corrections. But towards that goal, we have two approaches. One is so-called digital approach, where we're trying to explore the surface code architecture, and we use the X-Mon, G-Mon technology. While meantime, we also explore the so-called analog approach, where we're trying to build a quantum annealer, which we use the so-called fluxmon qubit we'll introduce you today. We think this route is a really attractive route because we think before we actually can reach a universal quantum computer, which may take us a while, we can actually use an analog approach as a test bed to test the devices as an order of 100 to a few hundred qubit. And more specifically, we wanted to build what we call Quantum Annealer version 2.0. We're hoping at the order of 100 to a few hundred qubit, we can achieve a performance that is good enough that can outperform classical computer. All right, but the real question is, what kind of quantum annealer you wanted to build? This actually is exactly the first question when we first met our theorists and when we plan to build our quantum annealer. So the answer for our theorists is very simple. First, when you try to build a quantum annealer, what you need to understand is what are the essential elements for quantum annealer. There's a coherence, there's connectivity, as well as a control. A best quantum annealer, what you want for, which we call ideal quantum annealer, of course, is far down along each axis, far away from origin as far as possible. And that's why they give you a long list. They will give us a long list which includes almost everything: high coherence, high connectivity, strong coupling, long stochastic, local, many, many things, as much as you can think of. However, as a hardware engineer, we say, hey, this is very challenging. Because in reality, we know that when you try to build something in hardware, we are facing a lot of practical constraints. So the quantum annealer we're trying to build will nowhere near the ideal quantum annealer in theory. However, now the question is where you want to locate this quantum annealer version 2 in this axis. You want to have more coherence or more control or more connectivity? This is really a hard question. But the other things you need to understand is the tricky part is along these three axes, they are not orthogonal to each other at all. There's correlations between each axis, and also different axes, different elements actually affect the performance differently. So you have to be very careful because the thing you're trying to build, you need to think about the system optimization. You cannot think about just individual qubit. You have to think about you're trying to build something that is suitable for the building a whole quantum annealer. So with that, I'd like to see, in order to answer that question, let's see what we understand so far. I guess all of you here knows quantum annealing, you can simply, in a simple language, think about you initialize the system in somewhere in the energy landscape, and then you involve your system, and hopefully by the end of the annealing process, you can find a global minimum. And the power of the quantum annealer, it is our common belief that coming from over this evolution process, if you have a quantum tunneling can happen, and that is where the computational resource coming from. In order to take advantage of quantum tunneling, so the problem that is really favorable for quantum annealing are those problems with high and narrow barriers, as you already heard many times in this conference. So if you have a high and tall barriers, this is where really the quantum tunneling can outperform the classical thermal activity process. So in other words, the optimization problem that is favorable for quantum annealing are those problems with rugged landscape and with many tall and narrow barriers. So to test that idea, as you may heard yesterday, so we have designed this so-called Wickstrom cluster problem. So we use a D-wave machine, and we choose 2 clusters out of the camera graph in their machine. And we apply strong field on one of them and weaker field on other, and we turn on the interaction between the qubit. During the annealing process, in order for the system to stay at its ground state, all the spin on the weak cluster, they have to flip all at once in order for the system to stay at the ground state. And what associated with this flipping process, if you look at the energy landscape plot on the right, you can see the system actually have to go from a false minimum, tunnel through a barrier in the middle, and go to the global minimum. It is this tunneling process we think we can find the computational resource, which is a tunneling process in this case. And we have proved both theoretically and experimentally, this process can be well described by incoherent tunneling. And the tunneling rate are given by this equation here. So if you experimentalist like me, and you should not be scared, because all you have to remember is there's 3 coefficients here that will strongly affect your tunneling performance. Those are related to your performance. So epsilon P, which we call reconfiguration energy, and W, the line width of your tunneling, and eta, the ohmic coefficient. We will come back to that. So the first take-home message we got in terms of how to build a quantum annealer experimentally is coherence actually matters. It will strongly affect your tunneling performance. And then with one pair of strong weak cluster understood, so we go to a larger array of weak strong cluster, which we call strong cluster network. In this case, now you can imagine instead of one tunneling event, you have many, many tunneling events. This is the case we think we can explore the real power of quantum annealer. As many of you already know the result, as one I show here on the left. So the result is actually pretty encouraging. The D-wave machine here actually did a pretty good job. Compared with symmetric annealing, as one you see here from blue line to the red line, D-wave machine really show a good speed up. In addition, you can see a scaling speed up if you look at the performance as function of problem size. Compared with quantum Monte Carlo, which is this green line, D-wave machine, of course, we don't see the scaling speed up anymore, but we see a huge 10 to the 8th prefactor speed up. So this is great news. However, there's something you need to be aware of is we know there exist other algorithms, such as Selby. You can really solve this chimera-like problem really more efficiently. You can solve that really quickly, and that can outperform D-wave machine. So what do we learn from this experiment? The message is, first of all, quantum annealer works. This is really encouraging, at least for certain problem over certain algorithms. However, what we really learn, in order to beat other algorithms such as Selby, we really need to increase the connectivity of your graph. In other words, you really want to build a graph that is much denser, such as you don't have any chip cut in your graph. So the second lesson we learned is we really want to improve the connectivity in our graph. And finally, I wanted to tell you this quantum parallel tempering you have heard from Hartmut yesterday. So without going into too much technical details, I want to emphasize this. We call it quantum parallel tempering, but however, it's actually a hybrid annealing process. We combine the classical parallel tempering with quantum annealing. We like this algorithm very much because now quantum annealer does not do the whole job. It only do what it's good at. It just whenever you need tunneling, it go for it. So as you heard from Hartmut yesterday, we're going to combine the classical parallel tempering. You run many copies at different temperatures. You update your system, as well as local swap according to the macroscopic rule. From time to time, when you need help from quantum annealer, you copy your information from classical processor to the quantum chip, and then you're cranking up your quantum fluctuation, the X field, and then cranking back down, goes through a hopefully goes through a quantum tunneling process. And then you look at your system and whether or not your system configuration is better, and then you accept or reject according to the macroscopic rule. In this way, you can combine both the classical part with quantum part and they all do its own job in the best part that they can. However, as a hardware engineer, the lesson I learned from this algorithm is, first of all, in order to be able to update your system quickly and accurately, you have to have a faster individual readout of each of your qubits. And then you can look at the configuration and then can do update properly. And second, in order to have information transfer from classical part to the quantum part, you have to be able to arbitrarily initialize your quantum chip to different initial state. So those are all the lessons we have learned so far. So let me tell you what is our current development in terms of hardware. So first of all, I want to introduce you the fluxmon qubit, which is a building block of our Quantum Annealer version 2.0. So it is still a flux qubit, as you might be familiar with. So we have a squid at the bottom here, and it's shunted with a coplanar waveguide as this meander line. So this is a qubit that we built. We think it's suitable for Quantum Annealer because let me show you some features. First of all, some of you may be more familiar with this conventional 3-junction qubit, as one shown here on the left. So if I put this conventional 3-junction qubit to our qubit and we scale them properly, you can see this is a much smaller size compared with our qubit. So the biggest feature of our qubit is very simple. We have a very big qubit. So why we are building a qubit in this way? The reason is we think the number one priority in building a quantum annealer is connectivity. We really want to build something such that is really enable us to couple many qubits together. So that's why we distribute our inductances, which is 700 picohenry over a very long distance, which is 200 micron. You can easily see this qubit really just by your eyes. So because of that, we distribute inductance over long distance. We have a lot of room to couple qubits together. We really believe the geometric inductance is a fundamental resource for you to couple qubits together. To give you an idea of what that means is, I want to give you a quick preview of the coupler we just built. It is being cooling down literally like right now. So of course, we have to verify this experimentally eventually. However, if everything goes correctly as what we design, we would be expecting this coupling between the qubit 1 and qubit 2 to be order of 1 to 3 gigahertz. And all these coupling strengths are actually given by the coupler in the middle, which only occupy a qubit space, about 10%. So this is great news, because now we have a lot of space to couple other qubits together as well. And I also want to emphasize the design of a qubit is also very flexible, because you can imagine instead of shunting your squid here with one coplanar waveguide, you can shunt it multiple of them. For example, I can shunt it 2, like the one I show here on the bottom. So the nice thing for this, if you shunted multiple of them, you don't lose anything in terms of relevant energy scale. They all stay the same as a single coplanar waveguide. However, now you just double your space. Now you have basically twice the space to couple other qubits together. So this is a nice feature, we think. So our qubit, in terms of control, is also very friendly in control. Because it's so big, now you can really put individual controls for every qubit. And then in this case, we have 2 of them. You can nicely put them at the 2 ends of the qubit, really far away from each other. And then we have dynamic control for each of them at the nanosecond resolution. So to give you, and also I want to emphasize, we also put a micro drive for one of them, at least right now, for the characterization of our qubit. To give you some idea, the control level we can have is we did a simple experiment, very simple, just single qubit annealing. We go from 0 to 1 in the x basis, and then we go to 0, 1 eventually in the z basis. We go through multiple processes and by control our system. So nice thing to have a nice control is now you can really arbitrarily choose any path you want from initial state to the final state. And if you choose a path that is good, you actually can finish the whole process within 20 nanoseconds with high fidelity, as the one shown here on the top. So you can see if I initialize my system, either in the 0 or 1, we have well-separated signals. And you can see some arrow here. Actually, those arrows are coming from the state initialization, which have nothing to do with the annealing process itself. So we are pretty confident we can control the annealing process in a rapid fashion with good control, with good fidelity. And finally, I want to talk about coherence. So coherence, it turns out, it's actually a pretty tricky problem to solve. at least from the 10 years of experience in our lab to build high coherent qubit like Xmon or Gmon, we know there's one important mechanism, loss mechanism, to affect qubit coherence, which is dielectric loss. That's why we built our qubit, instead of using lossy amorphous dielectric, we try to build our qubit crystalline sapphire substrate, which give us high quantity capacitors. In addition, we try to get rid of all the dielectrics, or for the crossovers, in this case, we replace everything with L bridges, as one shown here. And then we check our qubit coherence performance with a tunnel experiment with the number I show here on the right. And then if you compare the numbers with current, with D-wave meshing, unfortunately, I would say this is not a fair comparison because this is the number I can only find in the publication. I'm sure they have improved this thing substantially in the current design. So, but if we take a short comparison, we found out the ohmic coefficient, which is the one I showed, INTA here at the bottom, we have substantial improvement. And also the reconfiguration energy, epsilon p, we also see some improvement. However, if we compare the line width W here, we really don't see much difference. And in fact, if you rescale everything with persistent current, this line widths are actually worse than D-wave meshing. So what's going on? For those of you here in the audience who might be more familiar with T1, T2, so we also measure T1, T2 at different frequencies. So for T1, we measure from 1.5 microsecond all the way down to, say, 100 nanosecond, depending on the frequency. And for T2, we measure only like 45 nanosecond. This is nowhere near the most coherent qubit we have ever built so far, like Xmon. What's the reason? Actually, the reason is even though we get rid of, at least we minimize the dielectric loss, now because we built our qubit so big to maximize the coupling, we actually have to pay the price of increased flux noise. This is the price we have to pay in order to do system optimization to couple multiple qubits together. So to understand the nature of the flux noise, we actually did more careful measurement. We measured the flux noise at different temperatures. And we actually was able to measure both the symmetric part and anti-symmetric part of noise as a result I show here in the middle. So for the symmetric part of the noise at different temperatures, it really doesn't show much difference. However, if you measure the anti-symmetric part of noise, you can see actually it increases when you go to lower temperature. And it roughly follows 1/T relationship. So this is interesting because that means the nature of our flux noise having to do with the paramagnetic spins. And you will see more details in the talk given by Andrew in the afternoon. Of course, we're not happy with the coherence performance. We want to go even better. So that's two approaches we're thinking we can do in order to at least reduce the effect of the flux noise. First approach is you can simply reduce the sensitivity of your system to the flux noise. Unfortunately, that sensitivity is a persistent current itself. And this persistent current is one number you actually don't want to reduce because this persistent current is also a resource for you couple to qubit together. The stronger the persistent current will be, the stronger your coupling will be. So we think this is another route we're going to choose. Instead, as you will hear by our collaborator Robert in the following talk, we really try to work hard on the material research. We try to remove the fluctuating spins. We're trying to see where they are and how to remove it. So this is the route we're trying to do, and we will see whether or not we can do a good job there. So with all those understood, so let me go to my final section and talk about what is roughly a future plan about building the Quantum Annealer version 2.0. The nice thing to have a big qubit is now you really have a good time to design the graph. For example, for few qubit, I can give you a simple example how to build a fully connected network. As one show here, the black line here, so this the loop with the two cross, you can think about the squid and then one black line represents one qubit. And then to build a network with few qubit, you can just simply lay down qubit next to each other and then you bend your CPW and crossing each other. So in this case, you can really build a network with all the qubits coupled to each other. The nice thing for this design is you can really, because you have so much space, you can really separate your control part from your coupling part as well as the readout part. It's a really modular design. In addition, we have big qubit and small couplers. You can really put your controls, individual controls everywhere because you have space. And then you can really place them space out and then to minimize the crosstalk. And finally, I want to emphasize that because we have so much inductance, we really think we can have gigahertz coupling even for one qubit to couple to multiple others. Of course, we understand this architecture is not scalable because you will quickly run out of your space once you reach your connectivity degree. So what is the graph we really think to build? This brings me to this slide. So the goal for us to build a connected graph for our Quantum Annealer version 2.0 is, first of all, it has to be possible. In other words, the graph we're trying to design has to be possible to build in hardware. Second, it has to be practical. The graph you're trying to build can be used to solve practical problems. And finally, this graph had to be dense enough, complicated enough, such that it's not easy for the classical algorithm to solve. Our series figured out basically 4 figures of merit to look at this graph. You want to have small diameters, large conductance, not traverse. Of course, you worry about spin glass transitions. However, as a hardware engineer, my job is keep reminding them, look, we have hardware constraints. First of all, your qubit is a finite length. You have just enough space for you to couple qubits together until you reach the tolerance you cannot handle for the crosstalk. And second, you have a finite inductance for yourself. That means you can only couple one qubit to multiple others. There's a finite degree you can couple to. So with all those in mind, this is a graph we're proposing to build for our Quantum Annealer version 2.0. So I show you 3 examples from small size to medium size to large size. So here on each plot here, each color line here represent 1 qubit. So for small size graph, as I introduced you earlier, you can really think hard. We wanted to build an all-to-all connection. When we move to medium size, what we want to build is this so-called weaving-like structure. You can think about you have qubits spread out both vertically and horizontally. And sometimes you have those 90-degree bended qubits acting as interconnect. When you go to large graph, you still want to keep this weaving-like structure. However, now you need to introduce this long-range interaction somewhere in your graph. We call this neo-cortex because some of you may recognize this is actually the 2D graph for cortex. And if you talk to the spin glass expert, Helmut, he can tell you probably this is the only 2D arrangement that has a non-zero transition temperature for spin glass transition. And finally, for the hardware, we have a parallel effort. We're working on bound technology. We're trying to build our qubit on 2D planar geometry. And also, we're trying to build our control wires as well as readout resonator, everything else on the other. And then what you want to do is flip them together and do 3D integrations. And we really think this is the route we wanted to choose to scale up to tens or even hundreds of qubits. To summarize, I want to say the intermediate goal for us to build a Quantum Annealer version 2.0 is really to build these weaving-like structures for medium-sized Quantum Annealer. Of course, we have to understand at the basic level from single-qubit performance to small size devices. But the fundamental goal is here. It's a nice goal because we can hardwire some instance of optimization problem into this graph. And hopefully, we can demonstrate this Quantum Annealer can outperform the best set solvers. And if we have this working, and we can try to analyze and understand the scaling of the performance of a device. We really think this is a nice goal to hit if we can build such a Quantum Annealer, because for following reasons, if this annealer works, if this annealer doesn't work, we think this is the fastest road to failure because you should not expect this to work if you try to other problems, if you think about there's an embedding overhead. And this is easy to communicate even for the people outside the community. However, if this annealer works, we really think this can act as a stepstone. All you have to do is add a bunch of other functions such that it allows you to go to full programmable quantum annealer, which is open up to a wider range of optimization problems. And in addition, even in the presence of universal quantum computer, we still think quantum annealer can act as a more competitive choice because you have less overhead in terms of embedding. With that, and that's all, I'd like to thank everyone.
Thank you very much, Chen. It's perfect timing. We have time for questions, please.
So do you have any estimate how many couplings you can put on one fluxmon qubit?
Yes. So let me give you a quick estimate is this. So I said we can achieve this size of coupling we're happy with 10%. So you can take the simple take-home message for this design is you can couple 10 at least. Of course, this is our first design. We really didn't push hard on this design. So I think if we clean up some crosstalk issue and also go to the bump on technology, we think we can couple more. We are really aiming something for, at least for this single arm design, from 10 to 20, and for double arm, hopefully we can couple more. Yeah.
All right, next question, please.
Hi,
Yeah.
thanks for a nice talk. What type of coupling Hamiltonian can you achieve? And in particular, can you do non-stochastic coupling?
Yeah, I know
Sorry,
people can
obvious
ask
question.
this question. Yes, so the coupling we have been designed so far are basically ZZ coupling. Unfortunately, it's not non-stochastic. We also look at XX coupling. It is possible. Unfortunately, they are high-order terms. So in other words, whenever I have XX coupling, I naturally have ZZ coupling with much stronger strength. If we really want to have it, all you have to do is have ZZ coupling in the presence and use another coupler to cancel out the ZZ coupling. However, as I said, this is a very expensive resource. Unless people prove this is tremendously useful, we will do it. Otherwise, we will keep pushing hard on ZZ coupling. But another question is, if I give you a choice, say I can couple, say, 30 or 40 of qubit together, do you want that ZZ coupling, or you want to split it out into 20 ZZ and 20 XX? Which one you want? Because we don't know which one give us a better performance.
Can the XX be non-stochastic? Can it have both signs?
Yeah.
Can it have both signs?
I'm sorry?
Can the XX have both signs?
Oh, both sign? Yeah, sure. No problem. It's coupled naturally give both sign.
First, a quick question. Could you explain why the weaving is more efficient in space than the all-to-all? And second question, I was surprised that you didn't say anything about integrating error correction. So I was wondering if you have any thoughts about that.
Okay. Let's go to weaving. Of course, weaving is not as efficient as auto. That's for sure. The only thing is when you go beyond certain coupling degree, when we go beyond, this is for medium size. In other words, if you go beyond the coupling degree, you have to patch qubit together in a way such that it's possible for it to build. That's why we're building this way. We have to just slide our qubit horizontally and vertically, and such that I think the biggest feature here for weaving is you just want to avoid any cluster-like structures. We cannot keep building this all-to-all for many, many qubits because we're going to run out of the coupling degree problem. That's what we understand for the architecture. And for error correction, right now I have to say we haven't started thinking about it because now we just look at like small device so far. But when we have more device, yes, we will start thinking about error correction by going to logic qubit. Yes.
All right, more questions.
One question here, can I? Here.
Oh, okay.
Regarding the weaving, just follow up on the question of Daniel. So is the connectivity, or at least the average connectivity of every qubit increasing with the number of qubits or not? Or is it really 1-2D in some sense? I mean,
The
not 2D,
connectivity.
but fixed degree.
Okay. So you are saying you're asking. No, I'm sorry.
So
Can we be very specific? Like, what are the parameters you are thinking about in terms of diameter in your graph?
He's asking if the coupling degree increases with the number of qubits.
The coupling degree?
if you have 100 qubit, for example, every qubit is connected to 10, while if you have 200, how many qubits every single qubit can be directly connected with? Is it still fixed degree, the way you design
Oh, yeah.
the
I'm
graph?
sorry. Now I got. Yeah. So far, yes, it's fixed degree. Yes.
Okay.
Yeah.
And it is finite spin glass temperature proven?
For this graph, if we have enough like long range interaction, we do believe it's non-zero.
Okay.
The aim of supremacy over SAT solvers, do you have any idea of how many qubits you'll require for this?
For quantum, we are thinking we can achieve that probably on the order of 100-ish, yeah, roughly. We have to do careful calculation. Also, it depends on the coherence performance as well. Yeah.
Thanks.
A question about the coupling. Have you thought about the galvanically coupled qubits?
I'm sorry?
Have you thought about galvanically coupling the qubits?
Galvanic coupling is no different than mutual coupling. It's just the coupling efficiency is higher. However, you are facing a more serious problem in terms of parasitic coupling and crosstalk. So we don't think that that's the way we wanted to choose, right, at least right now.
Thank you.
Yeah.
All right. We are done.